or not. So now this there are device and non-invasive and pain-free. That's the reason people are uh, uh, showing interest to wearing these kind of diagnostic device for better. And of course, what is the advantage? So once you detect and you can use it for the you can for the treatment and all. So when you can start your treatment and you can prolong your lifespan. However, it is hard to embed these techniques in low power and order. So if you look at our typical weighted neural networks, if you are talking about MLPN and MLFFN, they are very hard to embed on under these circumstances. So what is the circumstances is talking about means it's a resource constraint, because whatever the variable device we are talking about is a resource constraint device where it has a limited capability, processing capability, limited storage capability, and of course communication capability. Now it is there. So in this direction, so what they did, the people thought of using a neural network, because the neural network is fantastic in mimicking the human brain. So that's why people are showing why don't we develop weightless neural network, a neural network without any weights in it. So then in that direction, there were two people called the Beldows and Browning. These were invented this weightless neural network, first time introduced this weightless neural network in the year 1959, and it is a breakthrough among all the neural networks techniques suitable for hardware implementation, because so we can easily, because there is no weights and we don't require any training, so definitely we will use it for the hardware, ideally suitable for the hardware implementation. The major advantage of this kind of network, this weightless neural network, are the easy of implementation and able to learn the single iteration. As I said, there is no weights means there is no training. It means that you require in a single shot you will get trained. The weightless neural networks are also called n-tuple classifier. There is another name, it's called n-tuple classifier. I will justify why it is called n-tuple. So these classifiers are offer fast training and testing performance. So they will provide what is called faster training and testing responses. So we can finish the training fastly. We can testing also obviously, because when you are implementing hardware, so the response is very good. The standard multi-layer feedforward neural networks, so say we are seeing the weighted neural network, stores the knowledge in the form of the weights. This we already know that to take any neural network architecture, the knowledge is represented in the form of the weights hyperparameters. Okay. But where unlike the standard neural network, our weightless neural network stores the data in a RAM. So in a RAM, so random access memory. So if you see the data is being stored now in a RAM, the data means your data set. I mean, the first version of the weightless neural network was designed by the Beldows and Browning in the year 1959, and afterwards there are so many people have attempted improving this weightless neural network. And all these implementation of the whatever the implementation followed after the first implemented by Beldows and Browning, all there are so many other variants of the weightless neural networks are there, but there are some commonalities among all these weightless neural networks. They are the interconnections in the weightless neural network do not carry weights. So that the one observation is whatever in weightless neural network take, its variants, so there is no weights between the connections. The weightless neural network can only take the binary input. It's because the data is being stored in the RAM, so it is accepts only the binary inputs. And the knowledge of the network is stored in the form of lookup table, so binary lookup table. So the knowledge, whatever the training knowledge we are saying, maybe even though it is required single shot, but that knowledge will be stored in the form of the lookup table or a hash table, you can say. Okay, lookup table, hash table. These weightless neural networks are simple for implement, and RAM is called a lookup. I mean, so if you want to search for something, the RAM will act as a lookup table. Okay, each neuron, so each neuron or here each neuron is nothing but the RAM. So here the RAM is called each. The number of RAMs decided by the number of neurons. Okay, each neuron are called RAM is having address line. So every RAM will have address line. So this address line is called a synaptic weights. Okay, is supplied with a binary bit string from the input pattern. Suppose what is happening. So this is my mathematical model. So here inputs I1 to IN. Here what is we are doing. So this is my RAM. This is my RAM. The input, so I1, I2, IN are binary in nature because these are address lines. So if I use 100, so they will go to the 100. What is there? It will, if it nothing is, it will store. Otherwise, it will pick up the same. Otherwise, it will override the information. Because it's a RAM, so we can, with the help of address lines, and so these address lines can get it from the data. Because you are converting input data into a binary, and this binary data will act as the address lines in the RAM. That's why the RAM is become now the lookup table. We are looking for some. So what is there in a specific address line? It is observed that the neuron RAM size grows exponentially with the size of input vector, because RAM size is always in the power of 2. So here RAM is nothing but what is the neuron, and the neuron size will increase exponentially with the number of inputs. Suppose the number of inputs is 4, it requires 2 to the power of 4. It can accommodate 2 to the power of 4 items, and you require. But if it is an n, then you require 2 to the power of n address spaces. That's why the size of RAM will, even though, so you see there are 2 to the power of n. The input is 2, but you may not require these 2 to the power of n spaces. So in that, what will happen? There are so many empty places will be there in your empty place will be there in your RAM. Isn't it or not? Suppose they are saying that there is a RAM. So this is 00 something, or all are ones here. So this is 2 to the power of n addresses. It means you can store 2 to the power of n. What if, what if, if, what if, what if we don't have 2 power n entries? Because if there is a RAM of size n, means it can accommodate, we can store the data related to 2 to the power of n items. 2 to the power of n items. If there is no 2 to the power n items, then what will happen? There are so many holes will be there. There are some blank places are left over in this RAM. So that's why there is no efficient utilization of the memory. So there is no efficient utilization of memory. So that's the reason, because the size is in the power of 2. So even if you increase 1 bit, even if you increase input size 1 bit, its value will increase drastically. Right. Now, as the WNNs proposed Bellows and Browning and suffers from the memory problem, which I discussed just now. To resolve this, Wilkes and with other friends has developed and proposed, and another variant of the weightless neural network is called Wizard. It is called Wizard. It's called Wizard weightless neural network. It is called Wizard weightless neural network. The wizard is identical to the simplest weightless network which I have discussed just now, except that the input pattern is partitioned into the multiple segments. So instead of storing entire fragment into a single RAM, because it is a limitation, because even small increase in the input pattern will drastically increase the number of places. That's why memory will be wasted. So what they are doing now, they are dividing into some segments or parts. Now for each part you are creating one RAM. For each part you are creating one RAM. For this you are creating. So the number of RAMs will be determined by the number of ways you are inputting or partitioning your given input. Okay. So Wizard is identical to the simplest weightless neural network, except that in Wizard the input data is partitioned into multiple segments. That's what I made. Right. Input is partitioned into multiple segments. So every wizard whitelist neural network is made up of several RAM discriminators, because here there is no one single RAM. So then there is a multiple RAMs will be there, and made up of several RAM discriminators, and each RAM discriminator is made up of one bit word RAMs. So what they are saying, that there are some set of RAMs in both for each class. So for each class you will have some set of RAMs. So this is called a RAM discriminator. This is called a RAM discriminator. So each 1-bit RAM that receives a portion of the binary input system or pattern along with the Y 1-bit word RAMs. Each RAM discriminator also consists the summing device. So what you are trying to say? For every 1-bit RAM, for every 1 bit there is a RAM. This 1-bit RAM receives a portion of the binary input pattern. Like n is divided into some segments, and this one part of the segment is going to the, so one of this what is called a partition, and along with the Y 1-bit word RAMs, each RAM discriminator also consists of a summing device. So at the last you will have a, will show that you will have a summing device which will accumulate the how many number of RAMs data is matching with the input data. So also each 1-bit RAM receives a portion of the binary input pattern along with the Y 1-bit word the RAMs. So the number of such RAM discriminator is equal to the number of distinct classes in your data set. So number of RAM discriminators is nothing but the number of classes. In the training phase, a binary pattern of Y into n bits is partitioned randomly. So because earlier in the very beginning version, the Y into n, so there is an input pattern. So you require how many 2 to the power of Y into n are required. That many places are there, and but if you divide into equal size of n equal size, each size is equal to the each size is equal to the y. So we are divide n. So each size so means we are partitioning randomly into y equal sized segment. Means so there is a y segments. Each size segment is n. So it's nothing but the y into 2 to the power of n. The total space required is the y into 2 to the power of n. So when compared to the 2 to the power of y into n, so which is much less than that. Hence, by using this approach, wizard approach, we can reduce the wastage of memory in a weightless neural network, right? In the training phase, a binary pattern of y into in the testing phase, the binary input pattern is supplied to each discriminator, and every discriminator provides a response in terms of the number of matches. So every discriminator will give the count of matches with how many number of RAMs it's getting matched. So these responses are evaluated according to the majority voting principle. Whichever is measured, the given data belongs to that particular class. So if you look at in the schema representation of our proposed approach, so there are multiple RAMs. So this is called one RAM discriminator. So for every RAM discriminator, there are multiple RAMs, and the number of RAMs will depend on the y number of RAMs, because so you have to divide into the length has to be there is a input of length n into y, and there are y segment, then each segment length is n. So something like that. So you have each discriminator is there, and a number of each discriminator will have certain number of what is called RAMs. Which these RAMs will act. These RAMs will provide the output, and this output is summed up at the summation device. Okay. On the right side, if you are seeing, you are giving a, so for all this data from y1 to the yn, the RAM 1 will be used, and afterwards RAM 2, and afterwards the last you will use the RAM C. Okay, so each and every RAM is having certain information, so to store or to accommodate. Okay, so at the last, once we storing, so whatever the training will take place. Also shown in the figure, wizard overcomes the limitation of simple weightless neural networks by dividing the y cross n size input vector into y segments. That's a major feat in your model. As a result, the total memory requirement is reduced from 2 to the power of y into, so y into 2 to the power n. This everybody knows. On the other hand, it lowers the generalization capability of the wizard. So what is happening is, if you are on the other hand, it lowers the generalization capability of the wizard. So when you are doing so, it will sometimes it may not perform the well and unseen data. That is called generalization capability of your model. Sometimes it lowers the generalization capability of the wizard. This caused applications using wizard performing lower than the virtual generalizing RAM (VG RAM). So that's the reason people are extensively using this VGRAMs and compared to this it is called Wizard RAM. However, Wizard has used to solve the problems in automatic video surveillance, robotics, and 3D video animation and texting categorization. Already, Wizard neural networks have been used for the following application in the robotics and surveillance and 3D video animation and text categorization. Now, so what is virtual? What is this VGRAM? So VGRAM is virtual generalizing the RAM. So the VGRAM, the virtual generalizing RAM, is a weightless neural network. Is a different from the weightless neural network which I have discussed just now. So we have very beginning I discussed a weightless neural network in which you have single RAM wheel is there. From single neuron we have reduced to the multiple neurons and multiple RAMs. Okay, neurons is nothing. RAMs. So during training, the VGRAM neurons store input binary pattern along with this associated class information. So what we have to store in this RAMs is, so along with the pattern you have to store the class information, especially in the VGRAM. So during the testing, each VGRAM neuron searched for the closest learned pattern using any distance measure such as the Hamming distance and so on. So we can also use Hamming distance to find the closest match and to measure by using ammunition we can find the closest match. The class information of the closest input pattern is the neurons. And what is the class label which we have stored in the during training phase of the closest pattern? So that class label is the final output. So the searching procedure of the closest pattern is sequential and requires scanning of each neuron whole memory, which is costly in terms of if there are many training patterns. So if there are so many training patterns, so task is a sequential process, means you have to come by line. So then that's it requires definitely huge number of huge amount of computation power is required. So moreover, the memory size of each VGRAM is increasing on par with the training pattern. So if the number of training records are more, the VGRAM is also having more number of training patterns. Even though the VGRAM weightless neural networks have these limitations, and these are used in many applications such as face recognition, text categorization, and traffic sign detection, which is there in your where it is the traffic sign detection, line detection, autonomous vehicles. Okay. So to deal with such problems like every neuron is having limited capability, and of course it's having limited the storage capability, and so this instead of the VGRAM, so we are going to propose a new neuron which will handle all these problems. Like to deal with such problems, a novel architecture for a weightless neural network is proposed. So what we did, we have proposed, it's our work, we have proposed a new novel weightless neural network. So that will certainly requires less amount of storage as well as the accuracy is on par with the weighted neural networks. So it uses variable size RAMs to optimize the memory usage. So what we have did is instead of having the fixed length of RAM models, we can have now the flexible value models. Here we can use how much you want. Okay. So it uses variable size RAMs to optimize the memory usage and a modified binary trie data structure for reducing the best time. So what we did, so in order to optimize the memory access and memory usage, the trie data structure have been proposed, and to reduce the test time, also we have proposed these weightless neural networks. In addition, a genetic we can also use for finding out the optimal mapping between finding the optimal mapping. We have used the genetic algorithm for the improving accuracy as well as the finding out the optimizing the weights. Like optimize not weight, there is no weights, but optimizing certain hyperparameters. Like here, what is the hyperparameter? Is the optimizing function, optimization or the mapping function. We have to find the suitable mapping function, so that will improve the accuracy of your weightless neural network for a specific task. Now, if you see when compared to the the first weightless neural networks, which was proposed in the 1959 by the Balduzzi and Browning. So now afterwards they have proposed another model called VGRAM, and then this is our proposed one. What they did is, so there is a binary input pattern and there is a mapping function. So this you want to optimize. Okay. So what mapping function I supposed to use so that the overall rest of the part will perform well. So for that, so we have used some other technique, optimization technique called genetic algorithm. Now let's go into this. Okay. So there is a RAM and RAM. There are n RAMs. So what are the typical contents of the RAM? So if you look at the typical content of the RAM, there is a one input, and a corresponding class, and there is a class access count. Okay, so what class actually it belongs to, and is there any other sub pattern or sub pattern which is matching to this particular pattern? So, okay, like this we are maintaining a we are getting this data, and this data is being organized in the form of the tree data structure. Okay, this. Now, the proposed architecture emphasizes on improving the classification accuracy by reducing the memory usage and finally reducing the test time. The first focus is on the memory usage, then if the memory usage is done, then we will go with the reducing the test time. To accomplish all these tasks, different techniques have been are used. According to the proposed architecture, the input binary pattern is mapped to the set of VGRAM neurons using mapping function for improving the accuracy. During the training, in each VGRAM neuron, the patterns are managed using trie data structure, and for the simplicity of the diagram, only the pre-access counts of each neuron are shown. The class information is not shown in the trie node. So this is a node called trie node, and the data structure is called trie the data structure. So when you store the data in a trie data structure, this helps us in the memory savings and faster access to the contents. During testing, each neuron output the class label. The final class label is determined on the base of the majority. And there are multiple algorithms are there. They are giving independent of classification. You have to combine all these to arrive at the final classification or class label. Now, as a part of our work, we also proposed in a VGRAM. So VGRAM, which is called a variable sized VGRAM, and this VGRAM or VGRAM, the slight variation of the VGRAM, where we have improved the in the it's compared to the VGRAM, the VVG is best because we are the size of the this VGRAM is a variable. So how much data you want to store, that much of information will be stored. If the VGRAM neuron stores both the patterns and its class information, what it does, if you want to store some data, it will store both the patterns and corresponding class level. Hence, its size is proportional to the training set. So the size of the VGRAM is proportional to the size of your data set. So usually count of such VGRAMs, such VGRAMs neurons needed and is undetermined. How many such neurons are required to fulfill our task, we cannot determine them. So proposed VVG RAMs optimize the memory usage. The size of each VVG RAM neuron is determined by a range of values that features can take. So here this is the first neuron is talking VVG RAM, first VVG RAM and first VVG neuron is trying to trying to optimize the memory usage by selecting this VVG RAM, because each and every VVG RAM is the size of each is proportional to the training data set. The size of each VVG RAM neuron is determined the range of the values that features can take. What is the features range values? Based on that, we can decide VVG RAM. However, also the count of such neurons is determined by dimensionality of the data. How many such neurons will be there? So that is determined by the dimensionality of the data. The motivation behind this approach is that every data set consists of some repetitive subpatterns. So why we are using this is the every data set is, I'm not talking about whole data set, but some subsets, some part of your data is having some repetitive subpatterns, but by eliminating these repetitive subpatterns, it is possible to constitute VVG RAM. So our idea is, so you want to remove this repetitive subpattern so that you can construct the variable size VVG RAM. The proposed VVG RAM neuron maintains extra information about the these repetitive subpatterns in the form of access count. So it not only does this VVG RAM neurons will also maintain an extra information extra information about these repetitive subpatterns in the form of the access count. So this extra information plays a vital role in decision making, and especially in case of ties. When there is a tie, we will resolve it by using some technique. So this is my right side is my proposed trie data structure. This is my actual trie data structure. So architecture of the VGRAM neuron and BBGRAM neuron have been shown in the figure 3 and B. Further, the proposed architecture employs the binary trie data structures to manage the pattern inside the VBG RAM neuron. So what we did, so this is my typical neuron, and so now let's see what the VBG neuron. So there is the pattern 00 zeros and which belongs to the class 1, and like this. So the class access count is 3 and the class access count is the 2. So whichever is a positive class belong to, then you have to say that. So what is the label of the class label when it's the class 1, or what is the its label when it's in class 0. So once we get this kind of distribution, the class distribution, the remaining process is very easy. So here there is a class C1, C1 and C2, C3 and C4. So okay, there are 4 class information are there and corresponding access counts is also there. From this finding of the maximum access count, we can see that we can so there are classes and manage the pattern inside the VBG RAM. So this is the proposed one. This is the existing one. This is the proposed one. We have introduced the access count. So finally, if you look at there is a mapping function, so which we need to optimize. Mapping functions map the input data to the synapses of the VBG RAM neuron. So where there is a data and this data you are transforming or feeding into the RAM. So this data you are feeding into the RAM. So if there is n bit binary pattern, there exists n factorial possible combinations. So if suppose if there is a binary pattern of n, so we can have an n factorial possible combination. To select optimal or near optimal mapping by doing an exhaustive search in a factorial combination is an MPR problem. Because there are n factorial possibilities are there, you have to find the objective value of each and every possibility. Then whichever is the minimum or maximum, accordingly we can pick the best solution. But hence this computational optimization problem is solved by one of the most familiar algorithm is called the genetic algorithm. Okay, so you might know something about genetic algorithm. So I will discuss at the last. Okay. So GA parameters have to be properly tuned to obtain the optimal or near optimal solution, and these parameter values are data set specific. So because these are called hyperparameters, and when you are fine tune hyperparameters properly, you can get you can find the near optimal solution and necessary values of the given data set. The objective function based on the sensitivity and specificity, which is defined in the page 1. Okay, so here the objective function which are more focus is on towards the improving the sensitivity and specificity. Right. It is clear from one that the objective function is a geometric mean of the sensitivity and specificity. So if you look at the objective function for proposed approach is the square root of the, or that is called square root of the, means the geometric mean of the sensitivity and specificity. Sensitivity focus only on the positive class prediction and does not capture any information about the how well the weightless neural networks handles the negative class cases. Similarly, specifically focus only on the negative class predictions and does not require any information about the how well the weightless neural network handles the positive classes. To balance both the positive and negative class predictions, a new measure have been introduced, proposed as a measure as a geometric mean of sensitivity and specificity. So this is the objective function. The objective function of is the square root of sensitivity and specificity. Sensitivity will talks about the negative class and specificity will talk about the positive class. Now, apart from this, improving the this mapping capability, the mapping function and its corresponding weights by using ML algorithm. So mapping function maps the input pattern to the synapses of VBG RAM, and this we already seen. And so usually in a standard VGRAM networks during the testing to measure the closeness of test pattern over the pattern stored in the neuron. So some patterns are stored in the memory and from human brain are called neural network. From this neural network, you are trying to fetch the data, the closest match. So that's what mean. Okay, so distances need to be calculated. How, because we want to find the how close they are, you have to estimate the distances, which is a sequential nature. As a result, the test time increases, and since hashing techniques is more appropriate for each and for search and insertion operation for each for each have used a hash table for the test time reduction. So some people also have used my attempts toward the hash functions in this same domain. So still hash tables are not an efficient solution as it increases the chance of the collisions as the number of entries are grows. So when the number of entries are grows drastically, this hash tables. Sorry. Still, hash tables are not efficient solution as it increases the chance of the collision as the number of entries grows. If the number of entries in the hash table increases, we can avoid the chance of the collision. So, moreover, it is desirable to design an effective hash function. Of course, when you are using the hash table, you require to an hash function to avoid this collision, but it is very designing a good hash function is very difficult again. It's another headache. Okay, hash function to handle this collision. So this imposes a computational complexity on the hash function. Hence, to address these problems, a modified version of the binary trie data structure has been proposed and it is shown in the figure. So we have proposed in a modified version binary trie data structure. So what this binary trie data structure will have the left child pointer and it has a right child pointer and it will have a prefix code. This is a prefix code and it is a class label and what is the class label actually and the access count of the class 0 and the class 1. So what is the access counts of the class 0 and class 1 and when there is a clash we will look at these access counts and these access counts will be maintained how many patterns are having this same sub pattern. Okay, what are the pattern we are following, how many and how many samples this sub pattern is existing, that is called a access count. So according to figure, every node of the binary trie data structure stores the pattern prefixes. So what the prefix and the class information along with the access count. So we will store the prefix code and the class information as well as the access counts. During the test, it finds the longest prefix match. We will use the longest prefix match algorithm for matching. The output of the each neuron is the class information along with the each class access count associated with the longest prefix match. So what is the output we will give when you are finding the longest prefix? So whatever is the longest, the corresponding access counts will be given. In case of tie, access counts of each class are useful to determine the class of the test pattern. Of course, in the tie, in case of tie, the access counts of each class are useful to determine the class of the test pattern on the majority basis. So unlike standard VGRAM neuron, the proposed VGRAM neuron, the neuron does not require any distance computation for the measuring symmetry. So earlier, we are finding the closest match by using the Hamming distance, but here there is no, we will use the longest prefix match for finding the match and corresponding access count. So as compared to the hash technique based earlier approaches, this binary trie version, the modified binary trie version is a very effective. Hence, this proposed VBG term neuron is efficient in terms of the computation. We can say because to reduce, we can eliminate the number of calculations that we don't have any hashing computations over here as compared with the standard VGRAM and hash technique based neurons. Now, these right and these proposed weightless neural network has been experimented on different kind of data sets to estimate the performance. So this has been experimented on the PMI and diabetes and lung cancer disease and diabetic retinopathy data set. And we have experimented on different kind of data sets, and these are some of the characteristics that will mention the dimensions as well as the data set size. So right. Now, if you want to compare, so I have to assess the memory requirements also. How much memory is consumed by each and every neuron. So we have to measure the memory usage of the wizard neuron. So how much is required in the wizard neuron, because in the wizard neuron, so you are dividing into S is divided into n parts. So you require 2 to the power of S by n into C into n. So this C is the number of classes, n is the number of neurons. And for each neuron, you require this much of bits. Similarly, when you are using VG neuron, so for VG RAM neuron, so this is the amount of memory is required. First, this is the VBG RAM. This is the VBG variable size VG RAM neuron. Here the RAM size is fixed, but here it is a variable. That's why it is much better than the VG RAM neuron. It requires less amount of memory. So so if you look at for the diabetes, if I'm looking at the diabetes data, so P minus and diabetes data, so the basal neuron requires 35 kbs of data, but in the VGRAM requires 31 kb, but it requires 21.25 kb. But there is a huge reduction in that. So in this, on the other hand, even if you take the test time also, it is taking less time because of what is called the modified binary data structure will provide the access counts, and when there is a time we can look into the other, we can get it. So now similarly we have found the access what is called time taken to for training and all. So this is taking less time. So even if they compare with the proposed on the state of the art weighted neural network, these are called neural weighted, but this is the weightless neural network WNN, but still it is performing better. Even yes. So here also I compared with the other state of the art. I mean, other state of the weightless neural network, but still it is performing better than the other state of the art also. So the similar lines, the data we have experimented our data on models on other kind of data sets are called lung cancer disease data sets, and these are some of the highlighted. The best results are shown highlighted, and if you look at on the PIMA, it is called lung cancer disease data set also. Proposed VNNs are performed by the standard VNNs. As not standard, the state are the weighted neural network. These are all weighted MLPN, MLFMP, and RBFM TD. So similarly for diabetes retinopathy data set too. Okay. So the same thing whatever we discussed, we have implemented in the hardware by using FPGA start and to create toolkit, and we can also realize it the same thing, because ideally these weightless neural networks are ideally suitable for the hardware implementation. So that's why we can, so wherever there is a hardware implementation is required, and in that hardware you want to make any decision making, you want to make the decision making, so there you can use this weightless neural network. Okay. So here we measure what is called the performance of this VGRAM and Wizard RAMs compared with proposed model. We have estimated the memory requirements in the lookup table. So how much power is required, how much area is required, how much time. So still the proposed is performing better than all the state of the art with this neural networks called Wizard and VGRAM. Right. So these are our references, and so let's take some 10 minutes break. Then after the break, we will resume our session with some other topic. Then we can close the FDP. Okay. At 3:30, I will close this. And so if you have any queries regarding this, please let me know. So these kind of networks, neural networks, are useful in the what is called edge AI. So when you want to, so when there is an edge device and there you want to deploy some AML algorithm, so this kind of neural networks are ideally suitable. Let's have some 10 minutes break. and we will resume our session.